So far, we've talked about representing integer values with binary sequences, but now we need to discuss how we can represent floating point values or decimal values by still using binary. And this is where the IEEE floating point standard comes in. By using 32 bits of binary in a very specific format, we can represent numbers like 3.375 in binary. So how does that work? The first thing we need to do is we have to take our number and we need to look at both what's to the left of the decimal point and what's to the right. We're going to take what's to the left and convert that to binary. And we're very familiar with how to do that. We just take the value and convert it as we've been doing throughout the semester so far. So 3 in binary is just 1, 1. Now the tricky part comes with converting 0.375 to binary. So if you recall back to when we first taught how binary works, we said that each digit in binary represents 2 to the power of some number. For example, the rightmost position represents 2 to the power of 0, then the next one is 2 to the power of 1, 2 to the power of 2, and it just increases like that. And then when we have a digit here, we take that digit and multiply it by the base. So for example, with 3, we had a 0 in this position and a 1 here and a 1 here, and we did 1 times 2 to the power of 1 plus 1 times 2 to the power of 2. Now, it pretty much works the same way when we're working to the right of the decimal point now, where each position to the right of the decimal point also represents 2 to the power of some number. However, when we were going left this way, we were increasing our exponents. So when we go to the right this way, we're going to be decreasing the exponents. That means that this position here is going to be 2 to the power of negative 1. This will be 2 to the power of negative 2. And this position will be 2 to the power of negative 3. Now you'll realize that these numbers are just 1 over 2, 1 over 4, and 1 over 8. So if we want to represent 0.375, we just need to figure out what combination of zeros and ones should go here such that when we add it all together, it equals 0.375. And you'll realize that 0.375 is actually equal to 0.25 plus 0.125, or 1/4 plus 1/8. So that means that our binary on the right-hand side of the decimal point is going to look like this. I'll write that over here as well. So now we have a binary representation of this number, but this isn't good enough because we don't want this decimal point. We just want one continuous 32-bit binary sequence. So the next step to forming that is to take a look at this decimal point. Right now this decimal point is in between this 1 and this 0. What we want is we want this decimal point to appear to the right of the very first 1 in the sequence like this. So in order to convert this number into this number, however, we notice that we're essentially taking this and shifting it over to the right. So we need to multiply this value by 2 to the power of 1 so that this actually equates out to whatever this is. Now we're almost done. We have all the information we need. We just need to put it into now the 32-bit format that IEEE floating point follows. So the way that that format looks like is, of our 32-bit binary, the leftmost bit is what we call the sign bit. This bit tells us whether or not our number is positive or negative. With a positive number, this bit here will be a 0. With a negative number, the bit will be a 1. Then the next 8 bits are going to be the exponent. And these 8 bits tell us information about this number here. Finally, the last 23 bits are the mantissa. And this is going to come from the values that appear on the right-hand side of this decimal point. So with the sign bit, we have a positive number here, so our sign bit's going to be 0. Then with the exponent bit, now it's not enough just to take this value here, convert it to 8 bits of binary, and shove that here, because we also want to be able to represent negative exponent values with our 32-bit binary sequence. So what we actually do is we offset our exponent value here by 127. What that means is we take the exponent value, we add the value 127, and we take the resulting value here and put that into the 8 bits here. So in this case, 1 plus 127 is 128. So these 8 bits are going to be whatever 128 is in the 8 bits of binary, which happens to be 1, followed by 7 zeros. Finally, the last thing we need is the mantissa. Like I said, the mantissa is just going to be whatever's to the right of the decimal point. So we're going to take these 4 bits and put it in the mantissa here. But you'll notice that the mantissa has to actually be 23 bits long. So what we're going to do is we're going to fill out the rest of the remaining bits with zeros to the right of what we had already filled in. So in the end, our binary sequence for 3.375 will look like that. Great, now that we know how to represent values in floating point, let's see what happens when we try to multiply them. If we have 2 values given to us in 32 bits of IEEE floating point, and we want to multiply them, it's a fairly straightforward process. It may sound a little complicated at first, but it's really not too bad. The 3 steps you need to follow are, first you need to figure out what the new exponent of your multiplied values would be. And the way you determine that is you take the exponent of the first number you're multiplying, and you take the exponent of the second number you're multiplying. You add those 2 exponent values together, and then you subtract 127. And the reason we subtract 127 is because both of these 2 exponent values both had 127 added to them. So if we were to just add them normally, then the resulting value would have too much of 127 added to it. So we need to just get rid of one of those 127s to make sure that we're still on the same offset level. The next thing we need to do is then actually carry out the multiplication of the mantissas. So we're going to take these values that appear here and just do a normal binary multiplication like we've done with project 1M. Then finally, we have the step where we need to re-normalize if necessary, and I'll get to that in a second. So in this example, we want to multiply negative 11.25 with negative 6.125. So following these steps, first thing we need to do is calculate the new exponent value. So the exponent of negative 11.25 is this binary sequence here, which calculates out to 130. And then the second exponent value is 129. And finally, we just need to subtract 127, and the value we get out of that is 132. So our resulting binary sequence, when we multiply these 2 values together, will have 132 in 8 bits of binary in its exponent field. Great, now that we've done that, we move on to step 2, which is taking the mantissas and multiplying them. So we take the mantissa of the first number, 0, 1, 1, 1, and we multiply it by the mantissa of the second number, which is 1, 0, 0, 1. Now, an important thing that we need to do, just level this out real quick. An important thing we need to do is we need to add this 1 to the end of each of these mantissas to the left. The reason we do that is because this is that explicit 1 that we had originally struck out of our mantissa section. This was that 1 that appeared on the left-hand side of that decimal point. So when we do our multiplication here, we need to add that 1 back in. Great. Another important thing to note is that I didn't really pay too much attention to how these 2 numbers lined up in terms of the fact that this 1 lined up with this 1 and this 1 lined up with this 0. It turns out that when we're doing this multiplication, it really doesn't matter what the position of the second number is relative to the first position. For example, I could do something like times 0, 0, 1, 0, 0, 0, 1, 1. And this should result in the same value that we get from doing this one. It's just that this will have more zeros to the right of the sequence. And it turns out that those zeros don't really affect anything. So let me quickly erase that. Now, like I said, we carry out the multiplication like normal. I'm just going to add these dots here so we know where these implicit ones were added. And if we carry out the multiplication, we get 1, 0, 1, 1, 0, 1, then I'm going to cheat a little bit and pull up the answer. The answer to this is going to be 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1. And you can, on your own, go through this math and make sure that I did it properly. If I didn't, you can come complain on Piazza. Now, the next thing we need to find out is where the decimal point appears in this number. And just like how we did when we did decimal multiplication in elementary school, the decimal point is going to appear in the position that is equal to where it appears in this number plus where it appears in this number. So for example, there's 5 numbers to the right of the decimal point in this number, there's 5 numbers to the right of the decimal point in this number, which means that there should be 10 numbers to the right, or 10 digits to the right of the decimal point in the final answer. And that means that the decimal point will end up right here. Right, so now we move on to the third step, which is this renormalizing thing. If it turns out that this decimal point does not appear to the immediate right of the leftmost one of the binary sequence, then we need to renormalize it so that the decimal point is in the right position. In other words, this isn't good enough for us. We want the decimal point to be in this position. So we want our number to be 1.00100111101. And again, in order to convert this number to this number, we need to add 1 to, or we need to do times 2 to the power of 1. And so because of this, we originally calculated our new exponent as 132. Now, if we were to convert this to the actual exponent value of the original number, this would give us 5. But because we need to renormalize it, and we renormalized it by multiplying by 2 to the power of 1, we actually have to add 1 to this exponent value. So our new exponent value actually, because of this entire step here, actually needs to be 6, which will give us 133 in binary, or 133 with the 127 offset. So in the end, when we're computing what the 32-bit binary sequence of these two numbers multiplied out is, we first take a look at what the sign bit is going to be. Because we multiply 2 negative numbers, the output's going to be positive, so we have a 0 for the sign bit. We have our new exponent value here, which in binary is going to be that. And then finally, we have our mantissa here. We're just going to move that down into the mantissa section. And fill out the rest with zeros. And now this is the actual 32-bit binary sequence that is a result of us multiplying negative 11.25 with negative 6.125. And again, you can try and convert this back into decimal and confirm the fact that that lines up with what these two values multiplied together in decimal are. Great, so we talked about how to multiply two numbers in IEEE floating point. Let's talk about how to add numbers. And you would think it's simpler than multiplication, but it's not. It is not too much worse than multiplication, but there's a few more steps we need to go through, a few more things we need to take into consideration than we did with multiplication. So, just like last time, I've laid out the steps that we need to follow for floating point addition. The first thing we need to do is we need to match the exponents of the two values we're adding. We'll see this later on, but if the two exponents of the two values that we're adding together don't match, we need to modify the lower exponent so that it matches the value of the higher exponent. And if we do that, then we will need to end up shifting the mantissa a certain amount to account for the fact that the exponent has changed for one of the numbers. Once we've done that, we can take the two mantissas and just add them, and that's just normal binary addition. And then finally, we take that resulting number, and we'll see if we need to renormalize it, just like we did with multiplication. Great. So now let's take a look at the example. In this example, we are adding 117.125 to 13.75. First step here is we take a look at the exponents, and we need to see if one of them needs to be changed to match the other. And in this case, we do actually need to modify one of these exponents. 13.75 has an exponent that is 3 less than the exponent of 117.125. So we need to shift the exponent by 3. And that means we need to shift this mantissa section over by 3 as well. So this mantissa section is actually going to turn into 0, 0, 1, 1, 0, 1, 1, 1, and then a bunch of zeros. Now the important thing here is this one here, right? If I asked you to normally just shift this over to the right by 3, you would just add 3 zeros to the left here. But that's not quite what we did. We added 2 zeros and a 1 here. Now this 1 is that implicit 1 that we've been talking about. So the first digit that we add when we do our shifts, when we're doing our addition, has to be this implicit 1. Then the rest can all be zeros. So this is very important. But now that we have our shifted mantissa, and now that our exponents match each other, we can go ahead and take these two values and do our binary addition. So we'll write out this mantissa here. So we're going to add the implicit 1. This here is the implicit 1. Just write that in. And then we'll fill out the rest of the mantissa. 0, 1, 0, 1, 0, 0, 1. Then the next thing we need to do is write out this number. But now we've already added the implicit 1 to this binary sequence, so we shouldn't add another 1 to the left here when we're writing it down here. Instead, we'll just add a 0. So this will be a 0. This will be the implicit 0, if you will, and then the rest of the mantissa that we calculated over there. So now, or back when we were doing multiplication, I said it didn't matter what the position of the second number was relative to the first number. However, with addition, it does matter because addition does change based on how much this bottom number is shifted, because now the bits to the right aren't always going to be 0, and that just gets messy. So now we do need to be careful that these two numbers line up properly. And you'll see that I just took this bit here and this bit here line up here, and then the second bits line up, and so on and so on. That's just how I went about lining these numbers up. But now that we have this, we can just go ahead and do our normal binary addition. And again, I'm going to cheat a little bit and just write out the answer. So this may take a little bit. 1, 1, 1, 0, 1, and then 5 zeros. And then a 1. Again, you can go through on your own and make sure that the math here is correct, but here's the answer. We have a problem though. So remember that the decimal point appears right next to the implicit 1 and the implicit 0 that we added to the number, which means that in our final sum, our final output, here's where the decimal point is. Just like before, this isn't good enough for us. We want this decimal point to be in this position here. So we need to renormalize our number. So this is actually, in order to convert the one number to the other number, we have to multiply by 2 to the power of 1. And just like before, this means that we do need to add 1 to our exponent. Our exponent for this new number that we are adding together was originally going to be just this value here, or whatever the matched exponent was, which was originally this value. But because we have to do this renormalization step, because we need to shift so that this decimal point appears in the right position, we actually need to add 1 to this. And so this is going to be our new exponent value. So finally, now that we have all this information we need, we can go through and actually write out the final binary sequence. So our sign bit is going to be 0. Our exponent bit is just going to be that over there. And finally, our mantissa is going to be this section right here. So 0, 0, 0, 0, 1, 0, 1, 1, 1. And then fill out the rest with zeros. And that, again, you can go through and convert that back into decimal just to make sure that the values line up. But that is essentially how you go about adding two numbers in binary floating point. Right, so the last thing we need to talk about is what happens if one of the numbers we're adding is negative. So in this case, I slightly modified the previous problem so that our 117 value is now negative 117.125, and we're adding that to 13.75. How do we approach something like this? Because now this negative thing is starting to throw things out of whack. It's actually fairly simple, except for one pretty major change to the established steps that we had before. The first thing we want to do is we want to determine of these two values, which one, and actually this should be a 1, we need to determine which one of these is bigger in terms of its absolute value. In this case, the top number is the bigger number, and we can easily determine that from the decimal value. Then what we're going to say is, okay, we're going to take the top number, and we're actually going to subtract it from the second number. Because negative 117.125 plus 13.75 is actually equivalent to what 117.125 minus 13.75 is in terms of absolute value. So if you can recognize that, all we have to do is just subtract the top number from the bottom number, and then make sure that in the end, the sign bit is set properly. So in this case, we're still going to do the whole shifting of the exponents to make sure they match, and shifting the mantises to account for that. And we're still going to be doing operations on the two mantises just like we did before, except the actual operation we do is different. Before we did an addition on the two mantises. Now we're going to subtract the two mantises in binary so that we can get a resulting number. And the subtraction is where things get a little fun, for a lack of a better word. So I skipped some steps just so we can get to this step here. Again, we did all of the previous steps already when we did the addition of these two numbers. Now we're going to subtract these two binary values. And at first, binary subtraction may seem a bit daunting, but we're really following the same steps and the same process that we do when we do decimal subtraction. The only difference is that now we're working in base 2 as opposed to base 10. And we'll see exactly how that comes up soon. So, just like with decimal subtraction, we just go digit by digit from the right to the left and subtract the two numbers. 1 minus 0 is 1, that's fine. And then we get to 0 minus 1. So now immediately things are starting to get a little crazy. If you think back to decimal subtraction, if we ever have a 0 minus another number, we'd have to turn that 0 into a 10 and then carry the digit from the next number to the left. We're going to follow the same exact process here where we're getting rid of the 0 and turning it into a new number so that we can subtract it from the bottom number here, except now that we're in base 2 and not base 10, the 0 turns into 2. If you want to know why it turns into 2, it actually turns into 1, 0 in binary, and 1, 0 in binary is the value 2. So we turn this into 2, and we have to carry that digit from the next digit to the left. So we have to turn that into 1. But in order to turn this 0 into a 1, we have to carry that digit from the next one to the left. So we have to actually take 1 away from this digit and turn that into a 0. But we can easily turn 1 into 0. That's fine, so we can stop there. So we go back to this 2 minus 1. So 2 minus 1 is 1. Then we do 1 minus 1, that's 0. And then we get to 0 minus 1. And so again, we have to go through this carrying process. We turn this 0 into a 2. We carry it from here, turn this into a 1. We have to carry it from here. And then now we can continue on with normal. 2 minus 1 is 1. 1 minus 0 is 1. Do some more carrying, so that turns into 2. That got to carry from there, which means we have to carry from here. And then we continue on. 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 1, and 1 minus 0 is 1. And we can put a decimal point here. So at this point, the decimal point is in the right position. It is 1 to the very right of the leftmost one of our binary sequence. So we don't need to do any normalizing here. We can just use the exponent that we had generated initially. And yeah, I'll skip the remainder of the problem from here because it's going to be the exact same as we did with normal addition. But the key thing to note is that when you are given a negative and a positive number, the first thing you need to do is figure out which one of these is the bigger absolute value, and then do that bigger value minus the other value. And then when it comes time to represent this in the 32-bit binary, just make sure that the sign bit is set appropriately. So in this case, the sign bit would actually be set to 1 because it is a negative